electric potential V can be obtained by solving the Laplace or Poisson equation. For example, we take the Cartesian coordinate to solve the Laplace equation. That means the Laplacian of V is equal to 0. So we have three elements, x, y, and z, equal to 0. But we only interested in solving a one-dimensional problem. That means we have only x or y or z component in our analysis. So it will be easier and less complicated, right? For instance, V only varied in x direction, so we choose only del square V divided by del x square equal to 0. So you have to solve the double integration of this form to obtain the general expression of V. Let's say we do the first integration. We got del V over del x equal to A. A here is basically a constant. Further integrate the expression, we got V equal to AX plus B. So we got another one constant. So basically the value of A and B can be solved by using the given boundary conditions. The solution for electrostatic problem, which is electric potential, can be unique for a specific region if uniqueness theorem is obeyed. That means when you are given the boundary condition and the area properties, so the solution is only one absolute solutions. Let's say you are given a region and you want to find what is the expression of potential inside the regions. You can solve whether using the Poisson equation and Laplace equation depend on the whether the charge system exists or not inside the region. A solution to Poisson or Laplace equation that satisfies the given boundary condition is unique. That means the only correct solution to the problem. By applying uniqueness theorem, obtain the capacitance formulation for coaxial cable or coaxial capacitor. Assume the outer plate is grounded while the inner plate is connected to the voltage source of V0. So let's say we have a long coaxial capacitor, right? This is not spherical, this is a coaxial capacitor. So we connect V0 to the inner surface. When R equal to A, we connect to V0. And when R equal to B, we connect to the ground. Between A and B is a dielectric where the rho V is not given. So we can assume as 0. When the rho V is 0, we can use the Laplace equations. So due to our coordinate system, which is cylindrical coordinate, so we take this element, okay? Why we take 1 over r d over dr, r dv over dr equal to 0? Because our capacitor and our potential is varying with r based on the figure. So we take the r element, and then you have to do the double integration for this expression to find what is the general expression of V. Okay, solving this, you got VR equal to C1 ln R plus C2. C1 and C2 is two constant that we need to find out. How can we obtain this? This is just a simple mathematics. When you bring R to the right hand side, it becomes 0. When d over dr we bring here, we got the integration of 0. You got a constant, C1. And then you have R here, you bring to right hand side, you got C1 over R. And then when you do another integration, you got C1 ln R plus another constant, right? By applying the boundary conditions, so we obtain when V R equal to A, we connect to V naught. So the V naught equal to C1 ln A plus C2. So we replace the R into A. Similarly, when R equal to B, we connect to ground. So we got C1 ln B plus C2. So you have to solve these expressions. Solving C1 and C2, we obtain C1 equal to V0 divided by ln A over B, while the C2 equal to negative V0 ln B divided by ln A over B. And we have to put C1 and C2 into the general expression, and this is your final expression. VR equal to V0 divided by ln A over B ln R over B. This is the VR inside our material between A and B. After you obtain the expression of V, we can find the electric field intensity E by using gradient. Okay, you have to refer to the table of gradient. This is the cylindrical coordinate. Because we deal with the variable R, so we only take the R component for the gradient. So we have to solve what is the dV over dr. This is your V. So later on you got E equal to, in the direction of R, V0 divided by R ln B over A. Next, we can find the surface charge densities at R equal to A and R equal to B. So you have to imagine when R equal to A, so is equal to dN equal to epsilon En. Because our material is epsilon naught, so we put here epsilon naught. So epsilon naught E normal, or E dot product is a normal vector to the surface. So when R equal to A, so basically the vector is going to the R direction inside the dielectric. So that's why N here is equal to positive R. So when you solve epsilon naught E R square A dot positive R, you got epsilon naught V0 divided by A ln B over A. This one R you change to A. For rho SB, it's also same with the dN. The only difference is here where the normal vector when R equal to B is going inside the material, which is negative R. And we have to change R equal to B. So when you change R equal to B dot product with negative R, you got negative epsilon naught V0 divided by B ln B over A. Next, find the capacitance. Capacitance is equal to Q divided by VAB. The VAB, the potential between A and B is equal to V0. This is the potential that we applied, okay, to the boundaries. So C equal to Q divided by V equal to epsilon naught 2 pi L divided by ln B over A. How to find Q? Q is equal to rho S ds. So at what surface? So Q is basically at R equal to A, because that is the higher potential. So basically from here, you have epsilon naught V0 divided by A ln B over A. You multiply with the surface of the cylinder, which is R dphi dz. You got this. Okay.